Good morning. HOD Professor A.K. Chaturvedi sir, my seminar guide Dr. O.S. Prajapati sir, seminar coordinator Dr. S.S. Gudara sir, faculty members, examiners and my dear friends. I Amandeep is pursuing my BTech in Aeronautical Engineering from University Department, Rajasthan Technical University, Kota. My seminar topic is Spacecraft Design and Analysis. This is going to be our list of contents. To start with the introduction, first let us know what a spacecraft actually is. A spacecraft is a vehicle that is designed to travel in outer space. It may be used for a variety of purposes including scientific explorations, satellite deployment and communications. Spacecraft can be manned or unmanned. They are typically launched into space using rockets, and once in orbit, they can travel to other celestial bodies such as planets, moons, and asteroids. There are several different types of spacecraft, including satellites, probes, rovers, landers, and crewed spacecraft. Satellites are designed to orbit the Earth or other celestial bodies and can be used for a variety of purposes, including communication, navigation, and Earth observation. Designing a spacecraft involves many different aspects and requires a multidisciplinary approach that draws on knowledge from various fields such as engineering, physics, material science, and computer science. Here are some of the key steps involved in designing a spacecraft: the conceptual design, the preliminary design, and the detailed design. Throughout each stage, engineer must consider factors such as weight, power, thermal management, and reliability to ensure the spacecraft meets its objectives. To start with the designing process, let us consider a CubeSat. A CubeSat is a type of miniature satellite that is commonly used for scientific research, technology demonstration, and educational purposes. A CubeSat is typically made up of multiple cubes called units, which are stacked together to form a larger spacecraft. To start with its designing process, CubeSat can be divided into six major subsystems, which are structure, communication, power, attitude determination and control, command and data handling, and finally the payload. Now let us further explore these designing processes. Firstly, the payload. In spacecraft design, a payload refers to the equipment, instruments, or other materials that are carried on board the spacecraft for a specific mission. The payload is the primary reason for launching the spacecraft, and the design of spacecraft is often optimized to support the payload requirements. The design of the payload will depend on the mission objectives and can include a wide range of equipments and instruments such as cameras, sensors, scientific instruments, communication devices, and more. The spacecraft itself must be also be designed to support the payload requirements. Structural design. The structural design involves designing the physical structure of the spacecraft to withstand the forces of launch as well as the harsh condition of the space. This includes selecting materials and designing the structure to provide the necessary strength and stiffness while minimizing weight. The structural design also includes considerations such as spacecraft center of mass and moment of inertia, which are critical for maintaining stability and controlling the spacecraft's altitude in space. Thermal design. Thermal design involves designing the spacecraft to manage heat transfer both to maintain the proper operating temperature of spacecraft components and to protect them from extreme temperature variation in space. This includes designing thermal control systems to regulate the temperature of the spacecraft and its components, as well as designing passive cooling and insulation systems to protect the spacecraft from extreme temperature variations. Thermal design considerations are critical for ensuring the reliability and longevity of the spacecraft. Electrical design. Electrical design involves designing the electrical system of the spacecraft, including power systems, communication systems, and control systems. This includes selecting components and designing circuits to operate in harsh radiation and temperature conditions of spacecraft, as well as designing redundancy and fault tolerant systems to ensure that the spacecraft can continue to operate even in the event of a failure. The electrical design is also critical for designing the spacecraft data handling and processing systems which are necessary for collecting and transmitting data from the payload. Propulsion system. Propulsion system provides the necessary thrust to accelerate the spacecraft and control its velocity and direction. The choice of propulsion system will depend on specific mission requirements and constraints as well as the size and weight of spacecraft. There are several types of propulsion systems that can be used for spacecraft including chemical propulsion, electrical propulsion and solar sails. Chemical propulsion uses chemical reactions to generate thrust while electrical propulsion uses electrical fields to accelerate ions or plasma. Solar cells are uses the pressure of sunlight to generate thrust. Control systems. Control systems are responsible for controlling the attitude and position of the spacecraft in space. This includes controlling the orientation of the spacecraft or its attitude as well as its position and velocity. Control systems uses a variety of sensors and actuators to measure and adjust the spacecraft's attitude and position, including reaction wheels, thrusters, and magnetometers. Control systems are critical for ensuring the spacecraft can accurately point its sensor and instruments towards its target and maneuver to different locations in space. Overall, propulsion and control systems are critical components of spacecraft design that are necessary for maneuvering and controlling the spacecraft in space. By carefully selecting the appropriate propulsion and control system to meet the mission requirements, engineers can design spacecraft that are capable of performing complex maneuvers and achieving mission objectives. Now let us explore with the other section of spacecraft design, which is the analysis of spacecraft. Analysis of spacecraft involves using various tools and techniques to evaluate the performance and behavior of a spacecraft. This can include both physical testing and computer simulations and can cover a range of different areas including structural analysis, thermal analysis, power analysis, propulsion analysis, and altitude and orbit analysis. Aerodynamics plays an important role in spacecraft design as it determines how the vehicle will perform during launch and re-entry. During launch, the spacecraft must overcome the forces of gravity and air resistance, while during re-entry, it must withstand the extreme heat generated by atmospheric friction. To address these challenges, engineer uses advanced computational tools to model the airflow flow around the spacecraft and optimize its space and surface materials. They also incorporate features such as heat shield, parachutes, and thrusters to ensure safe and controlled descent. Analysis is a critical aspect of spacecraft design and it involves using mathematical models and simulations to evaluate and optimize the design of spacecraft. There are several types of analysis that are typical performed under spacecraft design, including first, structural analysis. Structural analysis is used to evaluate the strength and stiffness of aircraft structure and to ensure that it can withstand the forces of launch and the harsh condition of space. This involves using finite element analysis software to model the structure and evaluate its stress, strain, and deformation under various load and conditions. Second, thermal analysis. Thermal analysis is used to evaluate the thermal behavior of the spacecraft and its components and to ensure that they can operate within their temperature limits. This involves using thermal modeling software to simulate the heat transfer and temperature distribution within the spacecraft under various conditions, including solar radiation, internal heat generation, and heat dissipation. Third, electrical analysis. Electrical analysis is used to evaluate the electrical systems of spacecraft and ensure that they can operate reliably in the harsh environment of space. This involves using circuit simulation software to model the electrical behavior of the spacecraft component and circuits and to evaluate their performance under various loads and conditions. Fourth, propulsion analysis is used to evaluate the performance of the spacecraft propulsion system, including its thrust, fuel consumptions, and trajectory. This involves using orbital dynamics software to model the spacecraft trajectory and simulate the performance of its propulsion system under various conditions. Fifth, control analysis. Control analysis is used to evaluate the performance of spacecraft control systems and ensure that they can accurately control the spacecraft attitude and position in space. This involves using control system simulation software to model the behavior of spacecraft sensors, actuators, and control algorithms to evaluate their performance under various conditions. Overall analysis is a critical aspect of spacecraft design that helps engineers evaluate and optimize the design of spacecraft to meet the mission requirements and constraints. By using advanced modeling and simulation tools, engineers can test and refine the design of spacecraft before it is built, reducing the risk of mission failures and improving the chance of mission success. To conclude with the topic, I would like to put some light on the future of spacecraft design and analysis. It is likely to be characterized by continued achievement in technology and a growing emphasis of sustainability and cost effectiveness. Some of the key trends that are likely to shape the future of spacecraft design and analysis include increased use of advanced materials. Advanced materials in material science are likely to enable the development of lighter, stronger, and more durable spacecraft materials, reducing weight and increasing performances. Second, greater reliance on electrical propulsion. Electrical propulsion systems are becoming increasingly popular for spacecraft due to their higher efficiency, longer operating life, and reduced fuel consumption. Third, growing use of artificial intelligence and machine learning. Artificial intelligence and machine learning are likely to play an increasingly important role in spacecraft design and analysis, enabling more efficient and accurate modeling and simulation of spacecraft systems. Fourth, emphasis of sustainability and cost effectiveness. As spacecraft exploration becomes more accessible and commercialized, there is likely to be greater emphasis on designing spacecraft that are sustainable, cost effective, and capable of supporting long term human presence in space. Overall, the future of spacecraft design and analysis is likely to be shaped by a combination of technical advancements, evolving mission requirements, and changing societal and economical priorities. By staying at the forefront of these trends and leveraging the latest tools and techniques, spacecraft designers and analysts can continue to push the boundaries of spacecraft exploration and expand our understanding of the universe. With this, I wrap up my today's presentation. So, thank you.